Hi, everybody. On topic 15, environmental stressors, we have subtopic 15.3, and this is a newly revamped material. And so I split what was previously here into a couple of subsections, just to kind of break it up a little bit. It was getting long otherwise. So this first 15.3 is on thermoregulation, how the human body adapts to different temperatures and effectively exchanges heat various, via the various methods by which heat can transfer. Okay, so first of all, there's a few numbers we know. I'm sorry I didn't convert these to Celsius, for additional, data points. But humans in the United States, we usually say 98.6 is what we expect on our thermometers, degrees Fahrenheit. But this can fluctuate and still have healthy people, up to 2 degrees. And even within ourselves, we have, over the course of a day, just due to normal circadian rhythms, we'll have a fluctuation of up to a degree Fahrenheit, in our body temperature. That's our core temperature. So, like if you had a thermometer at the center of mass, I suppose, but most closely approximated as in the mouth under the tongue, or the other body orifices, and then otherwise there's adjustment factors for the core temperature. But at the surface of our skin, it's not the same temperature throughout, so it's only 86 degrees Fahrenheit at the surface of the skin. Depending on the work that we're doing, are we just exercising? Are we relatively stable and not moving too much? Depending on that, we will have different skin temperatures. And part of this is because of the way that our bodies cool. One of the ways it does that is it essentially has more or less blood flow at the surface of the skin to have more or less of the internal body heat be dispersed at the skin, ultimately to cool the body. So 86 degrees is kind of that interface with the external environment. And the way this translates is, based on the internal metabolic activity and every other heat exchange that our body goes through. 72 degrees is kind of a rule of thumb, grand mean average, 72 degrees Fahrenheit for comfort levels in the United States, at least. When we deviate substantially from this, as low as 62 degrees or lower, this is when people, I guess, subjectively start, the tipping point is therefore they say they're cold. 78 and above, the tipping point says they feel hot. And so these ranges, kind of dictate office work, or indoor work at least. But humans interface in systems, in work systems, in all kinds of different contexts. That could be, the ambient temperature around you could be, significantly outside of this range. So that's what we'll be interested in here for the next couple subtopics. All right, so I think this is like thermodynamics a little bit, or maybe physics, but I'm just going to cover some of the basic ways that heat energy transfer occurs, and therefore the ways that the human body works with these heat transfer mechanisms so that we can thermoregulate. So effectively manage our internal, I guess, our body temperature so that all of our metabolic functions work properly. And so there's, we have to consider all these different ways that heat enters and exits our bodies here. So first, basic properties of matter here. We have conduction of heat energy, and I'm going to go into detail with each of these terms, but just to kind of get them listed here. Conduction, the most basic, I think. Convection, and we'll describe the difference, but there's a lot of similarities there. Radiation, which we've already talked some about, some forms of radiation. Electromagnetic radiation, aka light. But it also is, a general way for describing a way that energy particles emit and, their trajectory through space and all that, and how they impart, heat energy is similar to how light energy might strike something. All right, so a couple more heat transfer mechanisms humans are interested in. So evaporation. This is, a distinctly different way of managing heat, because effectively, I'll talk a little bit more about sweat here, but the idea of fluid being on the surface of the skin absorbs the energy, the heat energy of the surface of the skin, and then this facilitates this rapid, gaseous transformation of the water molecules, that is evaporation. So I don't remember exactly the strong difference between evaporation and like boiling, but you can look that up. That's outside of the scope of this class. We emit sweat on the surface of our body. It absorbs the heat of the body that helps transform that water into water vapor, I suppose, or evaporated water. All right, so conduction is the most basic. Convection, radiation, evaporation. I also want to note that when you're hot or cold, it can help to drink hot or cold liquids, I guess vice versa, right? So if you're hot, drink cold liquids, vice versa. But this isn't fundamentally different. This isn't, hot and cold liquids. That's a good way that humans thermoregulate, but each of these are basically a form of conduction and or convection. So we have these four basic energy transformations that we're interested in. Because, here's your thermodynamics. Because if our body temperature isn't rising or falling, it is consistent. That means our net heat transfer, our delta H, is equal to 0. We don't have any gain or loss in heat energy. It's all balanced. It's in homeostasis, so to speak. So we can look at this as a heat balance equation in terms of H being energy, change, which equals 0. But we have the metabolic heat. That's always a positive value. So that's, we're burning fuel in the presence of oxygen. There is energy, that we use then for producing physical work. We also have heat that's produced by that process. Then we have conduction. So what are we directly in contact with and then gain the energy or lose the energy? So plus or minus. I'm going to get into more detail on each of these. Gain or lose energy based on convection, gain or lose radiant energy, and then only loss of energy due to evaporation. Evaporation doesn't add heat to the system. It only removes it. It only cools. And so basically, if our delta H is 0, then we're at a healthy state. If we are above 0, rising, we are in a state of hyperthermia, too hot, and less than 0, hypothermia, too cold. All right. So each of these energy transfer basic mechanisms. So first, conduction. Look, I used a tall man lettering here, by the way. Go, call back to your displays episode, your displays topic, where we talked about, I think it was design for discriminability and the FDA project. So conduction and convection to me look very similar in a string of text. So I used the tall man, to try to make it a little more obvious. So this one, the most basic energy transfer is basically like a propagation of energy across molecules that are in direct contact. Okay. Yes, so propagation of molecules that are in direct contact. So if it's a continuous, medium, then the molecules within that medium. But also we have direct contact between this medium. So this is like a metal bar or something. That's also in direct contact with the human tissue. And so the energy can transmit effectively, across those direct contacts. So it depends on the material properties, depends on the temperature gradient, how hot is it here versus here, and yes, needs to have direct contact. This can occur between solids, between liquids or gases, any combination. So yeah, Jack here, freeze in the freezing water, and that lowering his body temperature is because of conduction of the very cold water directly in contact with his skin, pulling the heat energy out of his body. It's why we touch the stove after it's been on for a while. It's still hot. The contact with it is damaging. We actually have a lot of conduction in our everyday lives related to thermal regulation that goes through our feet, because of all of our body parts, our feet are most often in contact with a surface. And so that is how, if our body is a different temperature than the surface, then there is a gradient, then there is conduction of heat, to or away from the human body. Oh, very interesting. So thermal conductivity, so this is actually something, it's a material property, and there are sense of touch-based ways to infer materials that, it's going to seem really obvious to you now, but maybe you never put it in terms of, oh, well, this is the 630 concept that goes with this. But if you were to, run your hand over a wood countertop or a metal object, you can tell the difference in that thing. I mean, you don't even have to run your hand over it, just place it on top. You can tell the material, and a big reason you can determine that material without even looking at it is by how, like, the dynamics of how that material conducts heat away from your likely warmer skin surface from the surface of that object. So typically when we touch metal, we have more heat energy on our hands. We touch the metal. The metal is a high thermal conductive material. So we have relatively quickly that heat is pulled away from our hand. The sensation then, or what we feel is a cooling at the surface there. So touching metal feels colder, but really what we're feeling is a more rapid, essentially pulling the heat energy from the surface of our skin when we come into direct contact due to conductive heat energy transfer. All right, there you go. Okay, so if we want to be able to, think about this and design for human safety, performance, all that, some things we have to think about with really hot surfaces, or if we're trying to, impart heat in a most effective way. The surface area of the, how much surface is in contact dictates how much heat transfer occurs. Also the difference in temperatures between those two surfaces, but it's the direct contact that matters, and the more direct contact in terms of molecules, right side by side, the easier that transformation of, the energized molecules here then can energize these ones here. All right. And so if we want to limit that, and so like if we have surfaces that, may very rapidly cause tissue damage because they're very hot, we have, thermal insulating materials. So all of these are examples of things that are, resisting the transfer of heat energy from that hot surface to your, your flesh, basically. So protective materials here, great idea if you're handling hot things. That's the lesson there. Okay, good. Tall man again, right? So convection. So the previous was conduction, and that's about at the molecular level. It's about just the, the propagation of energy in direct contact with the next layer of molecules. Convection is, I think of it at least, as similar to conduction, but there's also then moving fluid. So this only works for liquids and gases, liquids or gases only, because you need to have fluid material. And part of the key thing here with convection is there is a transfer of heat energy between, so imagine here, in this boiling water here, the water molecules that are closest to the flame down here are imparted with heat energy or an increased amount of heat energy. And then because of the fluid motion of the water, those molecules rise, causing cooler molecules to sink. And then those cooler ones are exposed to the main source of the heat energy. So it's a little bit more of a, with time, an efficient transfer of energy. You're basically taking, all right, hey, energized particles that are right next to the heat source, get out of the way so there's room for the next cooler, set of molecules to come in and receive the same, heat transfer. So convection is essentially conduction with moving fluid of those surfaces that are coming into contact and transferring energy. So we have one of these at my house, a convection oven. And how that differs from a traditional oven is it uses some pattern of moving air to guarantee it's not just baking whatever's in the oven space. It is moving the air around that space so that it's increasing effectively the air molecules that are exposed to, I guess, whatever you're cooking, and transferring the that heat energy that way. So what I've learned then is our convection oven cooks things a little bit faster than a traditional oven, and that's due in part to more efficient energy transformation energy transfer because of the moving air around those surfaces. Okay. Interesting factoid here. One of the reasons, the reason that candles, when they're lit, or fire in general, has this shape where it moves upward, has to do with the fact that there are, atmospheric particles of air here that are energized when heat is added, and energy causes them to move upward while cooler air moves downward. And the flow of air that is effectively happening, at a candle-sized scale here, creates this sort of shape and look to a flame. If you don't have that moving air, and you don't have that moving air if you're in microgravity, because a big part of that, energized air is essentially more resistant to gravity. If you're not in a gravitational environment where molecules are moving relative to it, then there is no natural flow of air, even when there's higher energy states. So you light a candle in space, it doesn't show that same traditional shape because it's not showing the same convection related heat transfer that we see with this shape. Because again, that's the air moving in an atmosphere that is responsive to gravity. All right, so managing convective heat transfer, here's where we get to wear different types of clothing. So keep in mind that, we are typically working in, humans moving in space where we're talking about heat management, thermoregulation. Heat rises from the ground upward. So if you're going to conserve heat, protect your heat, you're going to want to contain it, as much as you can at the top. And so, there are hats that do this more effectively than others. Also, if you are extremely hot, working in hot climates, make sure you're venting your cabeza, right? So, all right. So, and if you are in hot context, loose and billowing clothes that promote airflow over the over the surface of the skin, this is a good way to encourage fresh air to be exposed to the hot body so that the heat transfer occurs. And again, just like a convection oven in reverse, when you have moving cool air, you can cool things faster. Just like moving warm air, I can bake things faster in the convection oven. So yeah, so we want to encourage air movement. We don't want tight-fitting clothes that constrain and kind of lock in the air, which is a very effective insulator and will trap that heat right in, against the body. So we want to encourage that heat transfer. We need more air exposure there. And then, of course, yes, turn on the fan, stick your head out the window to have more moving air over the surface of the skin. This is just facilitating, more and more heat transfer. I found something that says, up to about 2 meters per second. You go, faster than this as far as moving air, across somebody's body, and it doesn't have an appreciable difference. I don't know what 2 meters a second is relative to your average fan speed, but so anyway, in general, fans are good for maintaining relative, cool. And then air conditioning, and you probably know this, but air conditioning, aircon or whatever, is not the same as a fan. There's more to it. There is moving air aspects. There's also a cooling of the air, and there is a dehumidification of the air. And so these aspects all contribute to cooling, cooling mechanisms that work for humans, are various ways of heat transfer. All right, radiation, this being our third type. So, this is most easily sort of the example here is if you talk about campfire, and I think of the embers, when the flames are died down, but there's still a distinct heat that comes off these embers of fire, of wood, and you can feel the heat. You can also see them. They're basically glowing, and so what this is showing you is emissions of energy that are both in the visible spectrum. That's why they are glowing. That's why they're visible to you, and also in other spectra where it correlates with heat. Basically, how humans, all of radiation could be received as heat. There's a particular spectra in the infrared region, that is sort of a normal range of heat for humans to endure. We also maybe know this, infrared and infrared imaging, and this is, like a real technology, which can then see heat patterns, from humans, and different changes in the heat patterns might, relate to different health issues, maybe to different, sorts of cognitive states. That's an interesting thing to think about. But yes, so this is a typical range of heat emission in the electromagnetic radiation frequency range of 8 to 14, of wavelength range 8 to 14 micrometers. And so if you remember, I think 400 to 700 nanometers was the visible spectrum for the human eye. So nanometers to micrometers, I think we're going, I think we're on the order of several, 10 to the third greater magnitude wavelengths here. So it's a lower energy state, but it is emitting energy, due to body heat emissions, basically radiated body energy. This form of energy can be blocked with a line of sight. So this is when you see, people who work in extremely hot environments that have a lot of flame, have a lot of this sort of, heat energy source. This can make a really big difference in blocking with line of sight and fully reflecting all the radiated energy, that would otherwise be transferred as heat. Very good. Also keep in mind, so, here's due to convection, again, we have the heat most prevalent here at the head, heat rises. And this is also the most consistently exposed to the elements part of our bodies. So it also then is giving off quite a, that radiates the most heat. So another reason why, if you're in cold environments, try to protect your head first. This is for two reasons. The convection, heat goes up, plus the exposure. We typically lose a lot of heat through the head, the cabeza. All right. Oh yes, and when we have our head and torso warm, so if your hands are cold, don't prioritize hand warmth unless you have your head and your torso at a reasonable warmth level, because your body basically determines how much circulation goes to the extremities based on the internal temperature, in the core and head. So those got to be protected first. All of the heat is going to be conserved here, and only when that's at an okay level will the blood flow reach the extremities to potentially take the heat out to those less valuable peripheral body parts. Okay, so on the topic of radiation still, it's not just line of sight that we think about. There's also things like the surface, so the sun has heat radiation that is heat energy absorbed by this asphalt, and then that asphalt becomes at a certain level of heat energy, and it then will re-emit, re-radiate, some of that same energy back up, into the, into wherever. And so this re-radiation, this re-emission of energy is something that we have to think about beyond just that, hey, we blocked it with a really, nice mirrored suit, right? So, or, the line of sight barrier. So this is, for example, why we have insulation in the roofings, especially in buildings in Texas. Now, so this is interesting to me because my entire life before moving to Texas in 2011, I lived in colder climates. And so insulation was something I had dealt with, but in the realm of we got to be warm enough and hot air rises. And so we want to, keep that hot air inside when it's cold outside by building an insulation up in the roofing, of our house. Then I moved to Texas, and there's, I'm dealing with attics and things like that. So insulation is up there as well. And it didn't occur to me until until I started lecturing on this topic, that that's important because the roof itself absorbs so much sun energy. That energy is, that radiation from the sun is striking the most of the roof of my house, which is mostly absorbing that energy and then re-radiating it some into my house. And so a barrier of insulation in the rafters of the ceiling also keeps a house cool when it's really hot outside, and it's again blocking that re-radiation from the outside surfaces of the house. All right, so yep, promised we'd talk about sweat here. Yes, the human body uses sweat as one of its primary means of cooling. It is only a cooling mechanism. We never get warmer with sweat. We are always cooling off when we sweat. There's, you could say, oh, well, I feel hotter when I'm sweaty. No, because fundamentally how this works is there being any fluid means there is evaporation, means there is removal of heat energy from the body. And so that's the way it works. So the presence of sweat means there is a fluid in contact with the surface of the skin. Through then conduction, right? The energy is transferred to the fluid, the sweat, that encourages evaporation. Now there's that surface available for the next secretion of sweat, I suppose. So that is a way that we encourage conductive, essentially, heat removal from the surface of the skin. Each kilogram of sweat that would be evaporated, if it's by pure evaporation methods, this is 580 kilocalories of heat. So you can think about what that means. Remember, then this is like a 580 calorie, king size double Snickers bar, maybe. Burn that off with a kilogram of sweat, I suppose. You can facilitate the usefulness of sweat in heat removal by clothing wearing. And so sweat wicking clothing does this especially well. Yes, these are like gym shirts. They don't hold up as well as cotton-based shirts, but whatever their blend is designed to absorb the sweat that's being secreted by the skin and rapidly distribute it over the surface of the skin. More surface with more energy transfer via conduction means more evaporation. So these shirts actually help sweat do its job in cooling us off. So sweat wicking, there you go. Oh, and if we're going to use sweat, we need, fluid as input. We don't just, we can sweat to a point that there is no longer the ability to sweat. That usually means we're almost dead, and that's a very dire situation. So keep, you've been hearing it a lot lately with heat waves. It will probably continue to be something you always have to think about, at least in this part of Texas, is a serious risk of heat dehydration, heat-related dehydration. And so, yes, stay hydrated. Generally, the rule of thumb is don't wait until you're thirsty. You drink until you're, using the restroom, urinating about once an hour in especially hot heat. That's when you know your body has enough fluids that it's eliminated it via other ways. So yes, by all means, water most especially. And there's a little more to it than that. So don't wait until you're thirsty. Drink, especially if you're doing activities that are going to involve sweat. So I go out golfing with my son. I know I'm going to be outside for 2 hours. If it's Texas summer or not, there's going to be sweat involved. I'm always carrying, a good amount of fluids with me. Also, just keep in mind, so here's just kind of the severity here. 3 liters an hour can be lost in fluids if we're at our maximum, activity levels. If this equates to, 3%, actually it would be considerably more, if you didn't replenish that much. But 3% of your total body, your total water content, you start to have some physiological issues. 5%, we have heat exhaustion. 7%, you start to have, delirium. You're not, necessarily able to problem solve too well to help yourself out of a bad situation. And heat stroke, this is a medical emergency. And typically this is when people need to be revived, with careful rehydration. So no longer can be, taken orally, but there need to be, IV-based ways to rehydrate. So it can be very serious. Also, if you are in an environment where you're sweating quite a bit, you are losing some body salts with the sweat. And so there is a recommendation to supplement with the fluids with some basic electrolytes. So this is why, Gatorade or whatever energy drinks say, claim the electrolytes are what's helpful. It's essentially table salt, I suppose. I don't know, but it's just needs to have some sodium ions in order to maintain the balance of fluids inside and outside of the various tissues. This is what makes fluid available for cooling mechanisms, for the the viscosity of the blood and all of that. All right. Yes, so electrolytes do matter. 2 grams of salt per liter of water in extreme. If you're in the Texas sun, if you're outside for 8 hours in 90 to 100 degree weather, pay attention to not just drinking water. You have to have the electrolyte balance there too. All right, so I believe that wraps up this intro here on thermoregulation. So again, metabolic heat, our internal heat source. Conduction, convection, and radiant energy can be gained or lost. Evaporation is a loss of energy. If this equals 0, we're good. If it's above or below, then we have, potential stress conditions and ones that need to be managed if it's, if it's a human we care about, or if it's a workplace or otherwise. All right, thank you.